So with that, I think what I'll do is I'll start with today's talk, which is modelling and testing of Daly's Shaky Bridge. I'm Vikram Pakrashi. I teach in School of Engineering, and I'm also part of Engineers Ireland in Cork region. This talk is being jointly hosted by the Institution of Structural Engineers, along with Engineers Ireland Cork region, for the obvious subject matter, and then they were really interested in it as well. Before I start, the main thing I'd like to say here is, okay, I haven't included any mathematics in this, so which is a good sign, loads of video. At some point you might ask yourself, is this talk all about just looking at pretty pictures of Shaky Bridge? It might be true. And finally, one important thing that I'd like to emphasize here through this talk is how quickly and radically structural engineering is evolving into a new domain with interdisciplinarity coming from like really new and different domains from what we're used to. So with that, I think I'll start today's talk. As you see, this is the Shaky Bridge, and I actually didn't know about Shaky Bridge for the first 2 years that I was in Cork. Shame on me, but I didn't know about it. And when I knew about it, the question was, okay, should we try and test it? What are we going to do about it? Are we going to do analysis? So first of all, big thanks to Cork City Council, who gave us permission to do something on this bridge, and which is, of course, it was not invasive measurements, but non-invasive measurements, and we'll come to that when we get into a few more slides. So that's the bridge. It looks very impressive. It has a cultural significance here, not just in Cork, but in Ireland as well, and also in popular culture, in the sense, when I say popular culture, I mean the petrol station from where I fill my petrol. It has a massive picture of Shaky Bridge. It's on advertisements. It's in people's minds. So, and very haphazardly so. So this is a document from 1927. People who made Shaky Bridge, they started advertising it. There's been discussions in boards.ie. Hi, I was told there's something called the Wobbly Bridge, which is the Shaky Bridge, and pages of discussion about it. And then Irish Examiner says that there's been calls for urgent action to improve the condition of Cork's landmark Daly Bridge. I mean, I actually read this in Irish Examiner after we carried out these experiments and things like that, and it was quite interesting to know that, okay, people are thinking haphazardly about this. It's in our, collectively in our minds, and so can we use it in something? And secondly, because something is very lively, jumps up and down, do we really need to do anything about it? That's a question that we'll probably leave for later on, but let's start at the beginning, which is this. So this is the inauguration of Shaky Bridge, when it really started, and as you can see, there was, well, quite a bit of fanfare around it. And maybe I don't know, I can only speculate that people didn't expect it to be so shaky, or to be, all these complaints of discomfort or being afraid, still wasn't a part of the mindset, I don't know. And that's how it looked at that point of time, which is kind of like off Mardyke now. So if you have old pictures, I'd be more than happy to, make a little like collection of like these photographs of bridges, and even like we can take something up in terms of Cork bridges. So that was 1927, and this is 2015. That's not an advertisement paid by Murphy's in this talk. That's actually an advertisement on a bus stop taken. Shaky Bridge, officially the shakiest bridge in Ireland. So, I mean, that's not necessarily a bad public perception. I mean, yes, it shakes, it can be fun. I mean, I know of a bridge in Ireland where, now, probably there was a design issue, probably there was not a design issue. It became very lively, and I think it was called the Lively Bridge or something like that. So we can just change the name, and like we've done, we called Daly's Bridge the Shaky Bridge. Why am I suddenly jumping onto historical documents? Because when we started to model Shaky Bridge, we figured out that there were no drawings. There probably were drawings at some point of time. We can't locate it. It's just not there. So the next best thing you can do is you can start searching frantically, and these things popped out. So it's something that I was never a fan of, which is bill of quantities, and also something that I didn't particularly enjoyed working on when I was in the industry, but essentially this thing saved us. So we pretty much were able to recreate Daly's Bridge, or Shaky Bridge, it's easier to refer to as Shaky Bridge, from this massive document from where we could just recreate the entire drawing. And this is just a very simple drawing of the entire thing. Of course, we created the larger drawing, but this just gives you an idea of what kind of geometry we're looking at now, because this is actually the fourth, I think, one of the four like pedestrian suspension bridges in Ireland, and it's the only one in Cork. Now, of course, amongst the ped bridges, there's one here, and then the rope bridge in Northern Ireland, that's really lively, but this is one of the liveliest that you can, come across. So, apart from these like lengths of cables and things like that, the main span, that's about like 51 meters. That's quite high. So the main span is about 51 meters. There's the sag, the hanger spacing, tower heights, main cables. All these were available from where? So yes, we did go by these historic documents, but we actually went over there and measured it ourselves. That's something that works as a double check all the time, every time we start from the drawing. So this is a video that usually is shown at the end, but I think this is going to give us an appreciation of how shaky the Shaky Bridge is. That's a cyclist going past, because we're going to discuss the quantitative nature of all these things at some point of time. And that's a pedestrian. So it's good fun. That's the cable shaking, and that's Rob cycling. He's probably sitting somewhere here. He's sitting there. Anyway, controlled cycle test, he calls it. So one of the main things that we've done, other than as an initial work, other than like recreating the geometry of the entire thing, is just a general visual inspection, because when you're trying to model this, things may not be in the right condition, and we'll come to it in a few more slides. So what's the condition of Shaky Bridge? So what's happened is, yes, there's been some rust here and there. There's been some repairs over time, certain amount of, like small amounts of intervention, and so overall looks fine, but there are bits and pieces missing. And bits and pieces are missing because of corrosion. That's definite. So here's like some general snapshots of what's going on. As you can see, it's not great, but it's not the worst that I've come across. So what we have done is we have carried out a bit of surveying for the geometry and things like that, but why this piece is interesting, I'll repeat that again when we come to that slide, is Shaky Bridge shakes so much, the amplitude of vibration is so large, we could test for static deflections, we could test the bridge using a dumpy level. So a good old dumpy level, and a staff could test it in around 0.8 millimeters. You do it many times, take an average, and you're happy enough for the stability of the results that you're getting. So we have the geometry, we have the historic documents, so we have drawn something. What do? Like a good engineer, we start modeling this, and using finite element software, of course. So these are essentially, so this is a finite element model that we used. We used Strand 7, which is a commercial finite element package, and tried to recreate the bridge from its as-built version. So as you can see, this to this, this to this, and all that, this to this. And slowly the entire bridge was built in 3D, and we ended up with a model that looks like Shaky Bridge, and then the next expectation is that maybe it behaves like it. That's just a simple calculation with a point load, just to make sure that things are not moving in the way that we don't want it to. Now, of course, we need to do some standard checks. Like, we feed something into the software tells us something back. It may be right, it may not be right. The best answers are always what's found at the back of an envelope. And so if you do a basic model-based hand calculation for the self-weight of Shaky Bridge, you kind of get 37.34 kilonewton per cable from the finite element. Hand calc gives you 41.16. I'd say I'm happy enough with it, but if you disagree, I think we can discuss this after the talk. But that's the problem. I know what I've done, the software knows what I've done, the bridge doesn't know what I've done, doesn't know why. So it's essentially at this stage you'll think like, are we just going to look at pretty pictures of Shaky Bridge? And yes. So we test. Now the question is, what do we test? Do we test static? Do we test dynamic? What do we test with? How many? What for? Is it expensive? Is it dangerous? Should we just march up or like jump up and down? Like all these questions. And these are relevant questions because I've been asked before, like, how can you make absolutely sure you're modeling the bridge perfectly? I can't. I can be as reasonable as possible. And I need to get the statics right to get the dynamics right. So the question, the answer to all these things, like a good academic, is it depends. It depends what we're trying to do. It depends on the accuracy. It depends on what we're trying to achieve and whatnot. In this case, we started off by looking at the linearity of the structure experimentally. Yes, we are assuming everything is linear, elastic mechanics. We have great faith in it, of course. I have great faith in it. But does the bridge know about it? So what you do is you make up to 10 people stand at the midpoint of Shaky Bridge and keep on repeatedly measuring the deformation using that staff and dumpy level basic stuff like Stone Age stuff gives you a good answer. And what we found out is, yes, it's pretty much, it's mostly linear. And then of course we weighed them all and redrew the graph using Newton as the unit for horizontal axis. We don't measure like, deflection versus number of people. So that's something we've done. Once we were happy to a certain extent that this was working well, we started going into dynamic tests. This didn't stop our static tests though, so I'm going to come back to it because the dynamic tests again fed back to the static tests. Now, we couldn't make a hole into the structure, we couldn't test it, we couldn't load test it, so what we started doing was we started using wireless sensor networks over there of accelerometers. So these are like XB wireless accelerometers. They're really easy to use because you can just clamp them onto a surface as long as you're clamping them properly. It's picking up the vibrations of these things, and this antenna is, it just like sends all the data to the base station, and this is low powered, you can just work off a laptop. Loads of advantages, no cabling issues, takes away the health and safety issues there, all these things. And we started instrumenting the Shaky Bridge. Now you'll see that, well, we have clamped it with something over there, and because each bridge is very different, those clamps needed 3D printing, and it's one of these 3D printed clamps that we just made for Shaky Bridge specifically, and this was made in our lab. So it's not a very difficult thing to do. It's perfectly okay, to do it. I'll just pass one of these samples around to show it's just a very basic thing that was manufactured in UCC for this purpose. It was custom made. So as you can see, we have started instrumenting all these bridges with accelerometers, and then these are these 3D printed clamps, we had accelerometers here, 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 here. This was just in case something goes, like something's going wrong over there. If this thing is picking up more than that, which one is for the lateral vibrations, something we won't cover today. And then loads on the deck, because that's what we were really interested in for loads of occasions. Mostly in and around the midspan, and then in and around this quarter span. Now, that thing is interesting because that's a bet I had with students that I worked with. And they said that they're going to clamp an iPhone to the bridge with an iPhone vibration application. And I said, that's all rubbish, that's not going to work. And I think we bet each other 2 years or 5 years? 5? I know. Anyway, and the idea was, they said, yes, it's going to get something. So we'll see who won the bet. So that's essentially an iPhone clamped onto the bridge as well, as an extra one. Typical data, what you get is when someone crosses the Shaky Bridge, it looks exactly like one of those bridge data that you get for, you know, when people are crossing it. So here's someone like walking away from the bridge. We'll show more videos and it's going to make sense. So here's a video, start again, that discusses the acceleration responses first when we started measuring it or like modifying it in terms of instrumentation, because it's the acceleration that you feel in your body, and that's what makes you complain or doesn't make you complain. So you see that when the bridge is at rest and when a cyclist is passing it, it's really, really low. The acceleration is not much. The problem starts when people start crossing it, and of course when there's a group, because they're exciting the natural frequency and all that. So here's an example of someone, I think it's Deirdre crossing this time. There we go. And she has this phone in her hand because she's pacing her movement, so we know kind of when she was, at what point of time and all that. And these are all in meters per second squared. Now the question is, all these values, what do they mean? I mean, in simple terms. We'll come to that. Now the thing is, what's going on, if we get many, many, many samples of Rob walking over, Deirdre walking over, Vikram walking over, and all that, we can start taking the Fourier transforms of these signals and expect that the peaks are going to correspond to things that are related to Shaky Bridge. Now, there are two things that's related to the Shaky Bridge. One is its natural frequency, and B, Rob walking, Deirdre walking. This has a definite movement, and that frequency would be picked up here as well. So that's, let's say, Deirdre walking. I think both are Deirdre's walking. And from this is not an average of 2 samples. So from many, many, many samples, we were happy enough to say ballpark, the bridge natural frequency is 2.26 hertz. To what extent should you believe in it? To a good extent, but don't take the second digit that seriously, because what happens is over an entire day, the natural frequency of the bridge evolves with time to a certain extent, so it moves around a bit. Now the thing is, we'll go back to the acceleration. There are charts that say what amount of acceleration creates what amount of response in human beings. And our acceleration, no matter what the natural frequency or the walking frequency of the bridge was, falls between strongly perceptible and disagreeable. And if we start looking at our frequency in around 2 to 3 hertz, we are kind of pushing towards disagreeable. And if you remember, our pedestrian walking was in and around 0.6 region. I think we're hitting the disagreeable mark over there, something that when many people cross Shaky Bridge already have, they tell you anyway. So that's what's being picked up. So, it's true, probably. Correlation with other methods, because one thing that we did with Shaky Bridge was, apart from measuring it, modeling it, was can we use new algorithms, new methods of measurement, and use Shaky Bridge as a test bed for new ideas, new concepts. So first one, I called this, when we were testing it, I called that the rubbish concept, and this the good concept, and I'll discuss the implications of this later. But that was essentially the iPhone connected to the Shaky Bridge, which gave us a national frequency of 2.17 hertz. Remember, we got 2.26 after many, many, many observations. And we did a very new video camera based, we developed it with one of our researchers, Michael O'Byrne, who's sitting somewhere here today. And that technique picked 2.3 hertz. So I think I told Rob, took the bet with me. I told Rob I think I lost this bet. It was quite good, but the main thing to think about here is we're looking at really, really low frequencies. It's relatively easier for a slightly worse sensor to, through averaging these frequencies when they're dominant, when they're not corrupted by noise. If you go to the high frequency part of things, things start to get corrupted by noise, and then you need more sensors. I think what this slide is doing, it's opening up a debate that's going on right now, which is, can we use a small number of really, really high quality sensors versus a large number of relatively bad quality sensors, and the large number would take care of everything, and we just use big data. So let's take a look at the method that was developed as a part of this extended project for video-based monitoring. So there were different points tracked. You don't even need to go near to the bridge. Points tracked through a stereoscopic system that was made as a part of this project. We initially made it for underwater inspections, but then we thought, like, okay, we have a bridge here to test, why don't we try this? And we tracked the points and find out the vibration of it. So that's what we got from, let's say, video image processing, and it looks quite good. Now, I'm not going into the mathematical details of the algorithm. We can discuss it later on because it's quite involved. Here's a really, really interesting video made by Michael O'Byrne, who came up with the entire idea of, okay, this is how the algorithm would work. I think the video would speak for itself. Too many. And one great thing, as you can see in the video, we engineers might be good at mathematics, but we're rubbish in spelling. So what we do is, so here's let's say where it's standing is where the camera system is, and you focus at the midspan. So this is something live, and you pick a high contrast point so that you can track it. You need a contrast point. If it's too white or too black, you're not, with the background. Then there's a square window around it. Search in the neighborhood. And you follow that square window in successive frames, and the best match is related to what's known as a ZNCC. That's the name of the algorithm. Record the center point, and that can give you the vibrations measured, and that displacement in millimeters can be calibrated against the dimensions of the bridge that you already know. So you calibrate your images against a dimension of a bridge, and then you know what each pixel is worth. And then you can just take a Fourier transform of this image-based measurement, and you can find out from power spectral density what the natural frequency is. So this is something that's developed, implemented, and might be very useful later on. And what's more is it's been developed by a person who is from Cork. So the next thing that we tried doing with this bridge is, getting into a little bit detail here is a wavelet packet transform based technique. I'm not going into the details of wavelet analysis, but all I can say is we're trying to look at two things. One is, the bridge doesn't know how we are modeling it. We can only get outputs from the bridge. So we probably don't know what the model is. We have some control over, okay, this is how Deirdre is going to walk, but we can't get exactly what amount of force her legs are giving to the bridge exactly. So we have a vague idea about the input. We have some idea about the system, but we have a good idea about the output. So can we start detecting things from output-only systems? And wavelets are good because what wavelets do are like a little wave. They, in a very crude sense, they scan the entire signal in chunks, and within bounds of uncertainty in time or in frequency, they can tell you, okay, ballpark within a certain zone of time, here's the frequency that the entire thing is exhibiting. So what's the advantage of this? If you take a Fourier transform, you're averaging out the entire signal. So you lose all temporal qualities and you only get the frequency content. If you look at the time domain signals, you lose all the frequency content. The wavelet domain analysis lets you do time frequency analysis with some uncertainty bounds within this signal, so you can start telling in and around a centered time window what is the frequency content. With that, I'll actually move to figures. The problem that we are facing is, let's say when Rob's walking, and we deliberately did this, his walking was not coinciding with the natural frequency of the bridge. So we were getting two separate peaks in the Fourier transform domain. So it's easy to peak that peak and peak that peak, and we know, okay, that's the natural frequency. When Deirdre was walking, she was walking in a way so that it's very, very close to the natural frequency of the bridge. So what happens is, like two waves with similar frequency, they're mixing with each other, and then we don't know which one is Deirdre and which one is the bridge. The way we separated out the natural frequency from walking, of walking from the natural frequency of the bridge is using the wavelet packet transform. Let's consider for today's lecture this to be a new algorithm, whereby we'll look at the energy in the signal that we are getting, and those energy at different wavelet levels are resolved and packeted. Now what do we, when we talk about energy of signals, what are we really talking about? What we're really talking about is, just like any other energy theorem, the energy of an entire signal is preserved. So in a very crude sense again, if you take squares of any time domain signal, start adding them up, that kind of an operation is going to give you some value at the end. If you take the Fourier transform of that, again, start taking amplitudes of them, start adding them up, the squares of them, of course, that's going to give you another value. And for a signal, you'll see that these two values are the same value because it's the same information that's been moving from one domain to the other domain. So what we have done is we are using different packets of energy, and that clearly separates out Deirdre's walking and the natural frequency of the bridge. So if you were to use this as a black box, what you do is you invoke that algorithm when you're having difficulty in separating out people's walking from the natural frequency of the bridge, and it works really well. What happens really is, let's say you have someone walking at 1.8 hertz, and then you have someone walking at 2.2 hertz, and you can really separate out the envelope of pedestrian walking versus the random envelope that's been created by the structural frequency. But I'll probably leave out the technical detail of this and just leave it at showing how we separate out walking from what's really going on with the structure. And that's all from output-only observations. We do not need a model. We do not need an input. All we need is information from the structure. That's quite interesting. And then, of course, if we have more number of accelerometers, we can start estimating at mid-span, at quarter-span, what the mode shape is going to look like, and then we can fit curves to them to say, okay, this is how the normalized ordnance would look, this is how the mode shape is going to look. Here, it's not so good because we really had two sets of data that were very good. Ideally, if you have 8 or 10 sensors in and around this, with measurement for about a month or so, we can get really good modal identifications. We can even get the torsional ones. So, what about the model that we started off with? Because we did all these tests, now they must feed back into something. So, we either need to get the model right, or essentially we do it the other way around, because getting a model right is the most difficult thing ever. We just get the right model. We make some observations, we try to be as faithful to the observations, and look at how then the model starts getting closer and closer to reality. So, we had to use three main considerations for tuning the FE model. The first one was the diameter of the cable. There was some loss, so whatever we started off with wasn't absolutely perfect, so a small amount of change was necessary. Then, based on our observations and old data, because we started off with the Young's modulus of steel with 200, which wasn't it's okay for an initial observation. Then you start making it better. We had to change it slightly and see, okay, what's going on, and then we had to recreate the as-built damaged model of Shaky Bridge as faithfully as possible, with where Rob and Deidre were painstakingly taking note of every single defect that was there. So essentially we ended up with 5 different models. First one was the original model that we started off with. Then the next check is it our problem that we are not, is it subdivision and checking of elements, of course? Is it the problem with finite elements that's not converging to a certain extent, or can we make it better? Then there was a change of cable diameter. Then there was a damaged model, and a small change in the Young's modulus that we deemed necessary based on the historical documentation and our observations. So essentially that's what's being done here, Now, once you start tuning the model, what happens is the models, as we keep progressively increasing them to more and more complexity and detail based on what we observe, what's the correct thing, we start getting closer and closer to the field data in terms of static results in mid-span, in quarter-span, and these are all recorded static results. And those 2 lines are essentially best fit lines from our 5 theoretical models, and this is the one for the experimental model. But I think I'd go by the movement of these models that are going on closer, the models, how they move closer and closer towards the field data. So the dynamics have again inspired or fed back into statics. And as we kept changing these models, you see, because your natural frequency is directly related to the stiffness of the bridge, if we started off with our standard run-of-the-mill finite element, models, you're way off from what you're measuring in terms of natural frequency. As you keep getting better and better and better with what you observe, what you see, your assumptions, the sophistication of your modeling, you start getting closer and closer to the field data. Why am I not there, and why am I here? And that's because we exhausted all the reasonable assumptions that we could carry out based on what we have observed on the bridge, and we could go no further. Going any further would be a model fit. It wouldn't be a model making. So we just don't want to fit whatever that's coming out of the experiments. We really want to make a model that matches the experiments, and this has been the closest that we've been able to match. And we don't know what will make us go there. So the message is test and model, model and test. These 2 things should feed each other, back and forth, all the time. So that's mostly what we had for Shaky Bridge. But before I finish this talk, I thought I'd share some more quick slides with you, which perhaps gives us a slightly bigger picture of what we have achieved with Shaky Bridge. Because I really want these interdisciplinary things to be tested on such structures acting as a test bed for ideas. And maybe we can talk to anyone from Cork City Council if there's a way how we can do it safely and properly. So the larger picture is really about infrastructure networks. And the question, although I know there's been questions about, okay, what's going on with structural engineering? Is it still relevant because the market is down? The problem is, if we were to change our structural deficit anywhere, it's an impossible task right now. What we have to do is we have to do our very best to manage a large infrastructure where the needs are often conflicting with each other. And it's very important that it comes to our day-to-day conversation in practicing engineering in the academia, in assessing, maintaining, managing structures and infrastructure networks. How to do it, when to do it, what to do it, who is eligible, do we provide training for inspectors, training for assessors, where to intervene, how to manage it with priority, and the money, and essentially why do we need to do it to get this idea out there. And in most countries, because I've worked with some other places as well, I mean, these questions pop up every single time. Do we have an inventory? And yes, we have in most cases. Sometimes not so much in regional county councils, but I've seen many county councils actually like doing this. Say, for example, South Dublin County Council. Because that gives us their condition, gives us training to our people. It gives us analytical and experimental tools. And it also makes us, as a cohort, makes the government listen to us. Sometimes the industry lags behind, where, say for example, where the technology or the ideas have changed radically or rapidly. For example, I thought these two examples with the image-based thing and a wavelet-based thing would be two good examples for that. Then we need some demonstration test beds for people to be confident to use them. And maybe there's a role of the university over here, because that's going to dictate the kind of engineers we're going to release to the market. Because right now we're just not looking at, like, this bridge is owned by Cork County Council. There's an owner, there's a user, there's a neighbour, because if you affect one, the other person gets affected. It's a funding body, there's an operator and the society, and their interests may conflict, and this needs to be a part of a larger discussion. One of the main reasons is because we carried out a lot of studies with the European network with countries that were pre-EU and post-EU, and something that came up was a lot of bridges, a lot of public infrastructure built in and around that region, and you can see there's already a shift on the left-hand side of that histogram. So these are all aging. These are all aging to this extent. These are bridges, I'm not going to name them for obvious reasons, but I have tested myself. That's an underwater image, so that's not from Ireland, that's from Mount Harbour. I'm allowed to discuss this. That's something that's on public record, because this was a live testing that we carried out on a bridge that was hit by a low loader like this upwards, and we carried it out in around 7 or 10 days, but that's probably talk for some other time. That's a picture from a boat, I'm not going to discuss where, but I manually extracted the underside of the entire beam, which was supposedly pre-stressed concrete beam. So what I'm saying is all these things fit into a much, much larger picture of this infrastructure network management, and we need to be aware of this, and this needs to get into public discourse more and more for us to be able to manage this entire infrastructure network through inspection and testing, computation, and then a decision-making zone. So, to end, we have to embrace new approaches. Healthy, well-managed infrastructure network is a priority, and then investment into new approaches of assessing, testing, maintaining, managing is a must. And maybe with that, I'd like to thank everyone who's come to this session today, and I'd like to, before I take questions, acknowledge people who have been a part of this large project, because I think it's obvious to you, it's impossible for one person to do these things. So I'd like to thank Cork City Council, Deirdre O'Donnell and Robert Wright, who carried out a lot of testing and modelling, Michael O'Byrne for image processing, Ian Sadhu Michael O'Byrne, Bidisha Ghosh and Frank Scoof for image processing, Ian Sadhu for the wavelet-based algorithms, Fiona Edwards-Murphy and Emmanuel Popovici for instrumentation, And then we have Paul Cahill and Dennis Kelleher in finite element modeling. So some of these people are here with me today, and it would be great if they can just join me in this last slide so that you kind of get an idea of this is a part of a much larger project. Deirdre, Rob, because they worked a lot on this. Is Michael around? And then Paul. Did I miss your name there? In acknowledgements. So that's just a few of who we had, and there are more, and not necessarily all from Ireland. So with that, I think I'd like to thank everyone, and I think we can take questions. Thank you. Questions?
What conclusions did you come to? If, for example, there's no intervention, what's the likely lifespan? And if there was to be an intervention, would it be so costly that it might be better to replace the bridge? Possibly.
So sometimes I think you let it die. Yeah.
An order on it which won't allow it to be demolished.
Okay. I won't comment on, let's say, Shaky Bridge specifically on this, but usually what I think is important is to always consider a do-nothing option in all the intervention options. Because in loads of cases, the do-nothing option is good because you just let the bridge die. Now, there's a worrying trend, and for me it's a worrying trend, that what's done sometimes is, we go by the net present value all the time. Now with net present value with a 5% depreciation, it dissolves any activity that you're trying to do 20 years down the line or 30 years down the line. So let's say if you have 5 options and in your mind you know that this is the option I'm trying to go for, what you do is you reorganize all the interventions in a way so that a lot is dissolved in 20, 25 years, 30 years of time. So a lot of decisions are taken based on what's going to happen in 60 years' time, what's going to happen in 70 years' time. I think we need to move away from that, rather look at anything within, my recommendation would be in the next 7 years' time frame. And then I think we can take a much better decision on exactly what you said. Is this too costly or not? Because sometimes people do take that decision and say, okay, we'll let this die or not let this die. But what's going on is, after doing a lot of engineering, we engineers just use the net present value, which is decaying like this, 10, 15 years down the line. Whatever you start off with amounts to nothing. And everything gets, all these decisions they get dissolved over there. So that's something I think that I should. Yes?
Just when you were trying to close the gap between the modeled bridge and the actual bridge, national frequencies of both, is there not merit in just playing with the model to make it match and just use that as feedback then into your your coefficients and parameters that you know the 4 parameters that you use as your variables to change the output of the bridge, just to see like what just
you can do it. You can do it, and it's very tempting to do it. Why sometimes you shouldn't do it is because in a certain sense, it would be matching the experiment for the sake of matching.
Yeah.
It may not be what's going on with the structure.
I said first time round, saying you can take it so far, and knowing these are the changes that you can make and the definite reasons why you can make these changes. But like as you said as well, the bridge doesn't know what's been done to it.
Yeah. But your method works perfectly if the system of unknowns is in some way closed. But there are unknown unknowns in that system.
Yeah.
So we don't know what to optimize here so that we match the final. First of all, we have one, let's say, experiment that's going on. Let's say here's the vibration or here's the natural frequency that we're trying to close the gap with. But we have so many parameters that can be changed with so many combinations. There's no guarantee that there's a unique solution, A, and B, even if we get a unique solution, there's no guarantee that it's correct. There might be something else going on over there that's not obvious to us right now. So once it's obvious from a physical or say mechanics point of view, then we are happy enough to do that, exactly what you're doing. And in fact, that's what we have done here. But we kind of like stopped ourselves from the temptation of kind of matching and matching and matching, and said like, okay, till this point we're absolutely sure, okay, what we've done, we have some confidence in it. After this, we're getting into kind of grey area. So I just thought like, yes, we have done it. We kind of know like, okay, you tweak this, it matches, but maybe that's for internal discussion, and it's not something that I can stand over when I'm presenting. That's the main thing.
Yeah.
Can I add something there?
Yeah.
It was the natural frequency and the deflection of the model that we were matching as well.
Again.
And when it came to the natural frequency, it was constantly converging. But then when we look back at the deflections, they start diverging again. So you don't know what properties you're messing with when you try to match just one exactly. So
And deflection is something it's very, very, very hard to match.
So it's just bringing back to the model too, like
Almost.
the main thing we were dealing with really with changing the model was the boundary conditions. So the base of the towers, are they still fully fixed? Do we apply a certain release on the ink conditions? Another thing was like you could see that there was rust between members, So how much release do you apply to the nodes in the towers, in the parapets, and how do these affect the structure? And not only that, then you have the condition of the steel itself, which is a big question there. They would have been built in 1927, like you're kind of hazarding a guess and base it on historic documents that we got, and trying to get all these together and run a model. I suppose you can only get so far.
Absolutely, yeah.
Now that you've established the natural frequency of the bridge, is it an indication of how solid a structure the Daly Bridge might be in the future? Or is there a way of gauging any
From a global
structural
sense.
changes?
From a global sense.
Yeah.
What I'm saying is, when I mean from a global sense, is if there is a small amount of damage or localized damage somewhere, that's going to have very little effect on the natural frequency. If there has been a general, on an average, stiffness degradation of the structure, that's going to show up in natural frequency, because in very crude terms, natural frequency is stiffness divided by mass square root of that. So a stiffness loss would give you a lower natural frequency. If you start measuring the evolution of the natural frequency with time, that's going to be obvious if you do it for a long term. What's not considered here is sometimes what happens, as I said, over time, because of thermal effects, for expansions, contraction, there can be changes in stiffness, and that would give you a diurnal change in the stiffness of a structure. And then you're thinking like, okay, now do we have to deduct that variation? And probably we have to. Like if we get, let's say, permission from Cork City Council, that's something we'd like to do in summer months and see how it's evolving. Now, having said that, there's another way to actually find out local damages if we can catch the higher modes of vibration. For that, what we need good quality, but many sensors measuring things for a long time. By long time I mean many measurements, say hundreds of measurements. And then we can have a confidence on the natural frequency that we're measuring, because it's not a single point estimate. And then also the mode shape. And then the evolution of that would be indicative of the general health of the structure. So yes, it fits in with structural health monitoring. But if someone says like, okay, here's a small amount of damage, we've picked it up, take it with a pinch of salt.
Yeah. Now, the only reason I ask is, I suppose people look at the dramatic things in terms of total collapse, like Galloping Gertie or something, for
Right.
example. And I suppose on a more local level, people look at it and say, that bridge is rotten, like, by the time you did something about it, it doesn't look well, I think it painted it, or whatever. But lack of painting might mean, invasive corrosion, etc. That's the point I'm making is things have been likely to collapse, but it ain't great Nick either, is it?
I mean, collapse I think is kind of the ultimate state of structure. I mean, things have to go really, really wrong before they collapse. Now, one thing we might, again, as I said, like it shouldn't, it's not wise to comment on the safety of a certain structure that's owned by Cork City Council in a public lecture, but I'm not saying there's anything wrong with it, but we need to realise that, let's say if it's a matter of, yes, it's not collapsing, but yes, people feel a bit scared going over it, do we suddenly just stop letting it vibrate, or we just consider, well, this is a part of the culture of Cork and let it be a bit lively and just celebrate the Shaky Bridge as Shaky Bridge? That's something I think we can take a decision on. I mean, if it's good fun, I mean, why not? You know?
Was that point of Murphy's slide really emphasised the project? So just add to that comment as well is, you know, the structure is very flexible, you know. But if you stiffen up the structure, you know, it could snap, but bring it right back to basics. So it's very nice that it kind of moves and you know, there's some flexibility. So.
That's right, yeah. Wooden step. Yeah, sure.
Just on the materials of the day and where the sources you tap into to establish the reduced Young's modulus and was it, honestly don't know in situ testing none of the material, but are these readily available?
It's not like a lot of the inspiration behind a lot of these works was panic.
Yeah.
Panic and pressure was the main, let's say, driving force behind this.
Yeah.
So we tried like loads and loads of different things, and then once something worked, it worked. Ideally, if we could test it, it would be perfect. But testing comes with health and safety regulations, it comes with insurance and all these things. Just the health and safety for a day or two, it'll be like tens of thousands of euros sometimes. So we have to bear that in mind. So we want that's why actually we went for like wireless sensor networks and things like that. There's no cabling whatsoever, no like power requirement, just work off laptop and things like that. There's no stoppage of the bridge, so it's live and all that.
Actually, it's an interesting Rob and Deirdre at the start of the project. They used the original bill of quantities. They used the amount. They went back to the actual manufacturer of the steel, and they used pricing to the grade of steel that wasn't.
Yeah, we got onto the IC. We were months and months looking through libraries and different institutes, and in the IC in London, they actually had this very valuable document, the bill that was sent to it was William Farrington, I think was the Cork City engineer at the time, and there was the bill that was sent to him back when the bridge was finished. And it actually had the bill of quantities, which was invaluable, and it also had, I think there was about 12 men working the bridge and the B&B costs and everything, so I think it was about £500 for each. It was a fairly interesting document. So yeah, a lot of our assumptions were based off that. Another valuable document we got, Vikram spoke with earlier, was so the bridge was built in 1927, and David Rowles released their Bridges magazine in 1933, I think. And so you can actually look up the bridge or the magazine, pick your bridge, then there's a table at the end. You pick your span, pick your width. You basically buy the bridge, the land on, and put it together. You know, it's like they were like a flatback kind of company, but in that then they were just talking with the members used. And back to your question about the materials, so they find that steel was the main component there.
So I think we can take it up because it's 19:59 and we finish at 8. So I think we can take up any other question offline. And
if I could just say on behalf of the Cork region of Engineers Ireland, Vikram, we are delighted to be here in UCC, and I'd like to thank UCC for hosting this. It's been some time, I think, since we've been here, and it's a great